So this is the second video in a series of videos that we will be looking at that have to deal with theorems and proofs about determinants of matrices. A couple of things. I will assume, first of all, that you've watched the first video, and also I will assume that you have looked at the first problem on what I called the determinant proofs preparation page. That is that I have taken a 2 by 2 matrix, labeled it as A, B, C, D, so that means that I've just looked at every single 2 by 2 matrix, and then I've asked you to evaluate the determinant of E times A, where E are all of these 5 different choices, and then the determinant of E times the determinant of A. And what you should recognize is that I use the letter E because these are elementary matrices, and also these are every single elementary matrix that we can have for 2 by 2s, right? So letter A is the one that involves swapping the 2 rows. B and C have to do with multiplying the first or second row by a value of k. D and E are multiplying a row and adding it to another row. So essentially what we've done here is we've taken every single matrix and every single row operation that can be done on that matrix. This is a pretty straightforward assignment, and so we will again assume that you have done this before moving forward in this video. So the thing that we would like to prove is how row operations will change the determinant of a matrix. And so this is a theorem where if we assume that A is a square matrix, then if a multiple of one row is added to another row to produce a matrix B, so basically I'm saying that you take A and you do one row operation and create B, and in this part the row operation is multiplying by a row and adding it to a new row, then I claim that the determinants are equal to each other. If you do a row operation on A multiplying a row of A by K to produce B, then that is going to multiply the determinant by K. And lastly, if you swap 2 rows of A to produce B, then that is going to introduce a negative. That would be the same as multiplying the determinant by a negative number. So this is a theorem, and the way that we're going to prove this theorem is actually using elementary matrices. So I can restate the theorem in terms of elementary matrices by saying that if A is an n by n matrix and E is any n by n elementary matrix, then the determinant of E times A is equal to the determinant of E times the determinant of A. You may recognize that in the last video when I was setting the stage for the things that we are going to do, one of the things that we will do is prove that the determinant of a product is equal to the product of the determinants. This is not that proof because here I'm making a specific case of A can be any n by n matrix, but E is only allowed to be an elementary matrix. We will use this proof in order to prove that proof, and that's coming up a little bit later. So I've said that the determinant of E times A is equal to the determinant of E times the determinant of A, where the determinant of E is either 1, -1, or R, depending upon what the row operation was. So if it's a row replacement, that is multiplying a row and adding it to another row, then you don't change the determinant. If you're just swapping 2 rows, then you multiply the determinant by a -1, and scaling by R is multiplying multiplying a row by a scalar. And again, I said it on the last slide, but that B is E times A. Do exactly one row operation on the matrix A to produce B. Okay, so the proof is going to be done by induction on the size of the matrix. And so induction has got 3 parts. We show that it is true in the first case, then we assume that it is true in the kth case, and then use that case to show that it is true in the k plus first case. Okay, so for us, the first case is 2 by 2 matrices. Certainly, 1 by 1 matrix, we could talk about that, but there's no, there's 2 of the row operations you couldn't do. So a 2 by 2 matrix is the smallest matrix where you can do all 3 of the row operations. And you should notice this, that we've actually already done it. That in the determinant proofs preparation problems, that's what you did. You took every single 2 by 2 matrix and looked at every single row operation that could be done on those on that matrix. So we have taken care of all of the 2 by 2 cases. So in our proofs by induction, that takes care of the first case. Now we assume that it is true for all k by k matrices where k is at least 2. And then we want to use that assumption to show the third case, which is that if I look at k plus 1 by k plus 1 matrices, that this will be true. And I'm going to use the notation that n is equal to k plus 1, so I can, from here on out, refer to A being an n by n matrix. So really, the bulk of this proof, as with all proofs by induction, is going to be about the third case. So what we do is we recognize that we're only doing one row operation, and the row operation that E does on the matrix A is going to leave at least one row unchanged. Remember that K is at least 2, which means that N is at least 3. So we're talking about matrices that are 3 by 3 and bigger. And for all those kinds of matrices, at least one row is left unchanged by a row operation. If you swap 2 rows, there's a row that didn't get swapped. And what we'll do is we'll look at cofactor expansion along one of the rows that is left unchanged. So I'm going to say that the ith row was left unchanged, and we're going to do the cofactor expansion along that row. All right, so the rows of Bij, and recall that Bij is the cofactor when we cross out the ith row and the jth column. They are obtained from the rows of Aij by the exact same elementary row operation that E performs on A. So again, just if I was to imagine an example, maybe it's a 4 by 4 matrix where I'm swapping row 1 and row 2. That means that row 3 is left unchanged, and I do cofactor expansion along row 3. Well, all of the cofactors will be 3 by 3 matrices, and in those 3 by 3 matrices, we're going to be swapping the first 2 rows. So Bij and Aij are going to have the exact same thing done to them. Okay, so since Bij and Aij are only k by k, our inductive assumption works. Again, in proofs by induction, we always have to use the kth case to prove the k plus 1 case. So our inductive assumption implies that the determinant of the cofactor is equal to alpha times the determinant of the other cofactor. The cofactor of B is changed, so we change the cofactor of A by multiplying it by alpha, where alpha is equal to 1, -1, or r, depending upon what that row operation is. Again, k by k, so my inductive assumption applies. All right, so the cofactor expansion along the ith row of E times A is given by, and so then I've got this big set of equations. This looks a lot more complicated than it is. The determinant of E times A, well, E times A is equal to B, so that's the determinant of B. And we're going along the ith row of B, so J, the index, is going along the columns. And so you'll notice that all of the indices start with I because we're moving along the ith row. So Bij, I plus J, Bij. So the lowercase b is that thing that has been crossed out both times. -1 to the I plus J, it tells us what the sign would be, plus or minus. And then this is the determinant of the cofactor. All right, so then moving from this line down to the next line, all I've done is replace the Bij with Aij, which I'm allowed to do because we're moving along a row that has not been changed by the row operation. So that's the only thing that I changed there. Then moving down to the next line, I am replacing the determinant of Bij with alpha times the determinant of Aij, and I assume the determinant of Bij is alpha times the determinant of Aij. And then moving down from this line to this line, all I've done is taken the alpha, which is a constant, and factored it all the way outside of the sum. And then what I'm left with is this, which is the determinant of A. So all that going together, What I have is that the determinant of E times A is equal to alpha times the determinant of A. That's a lot of math. And the last thing to note in the proof is that if we let A be the identity, then we get that the determinant of E is equal to alpha. If I go back to the previous slide, if I was to let this value, this A, be the identity, then we know the determinant of I would be 1, so I would get that the determinant of E is equal to the value of alpha, and that was the last part of the proof.